Question 7. Chlorine is used to decrease the numbers of microorganisms in water. So it kills germs in water, both in drinking water and in swimming pools. In drinking water, you have to be careful with the amounts. Don't use in small amounts because chlorine is toxic. When chlorine is added to water, there's a redox reaction. So there's reduction and oxidation going on at the same time in the reaction. As shown by the equation, Cl2 plus H2O goes to ClO plus HCl. Fine. Deduce the oxidation states of the Cl in HClO and the oxidation state of the Cl in HCl. Well, oxygen's -2 oxidation state, because it's in group 6 of the periodic table, gains 2 electrons and becomes 2 minus. H is in +1 oxidation state usually. Occasionally it can be a hydride ion and gain 1 electron and be in a -1 oxidation state, but most of the time it's in a +1 oxidation state because it's got 1 electron in its outer shell and loses that to fill up its outer shell. So the H is in +1, the O is in -2. +1 minus 2 leaves -1. Now there's no charge left over, so I'm looking for a number that -1 equals nothing. So Cl is in +1. So the H is in +1, the Cl is in +1, the oxygen is in -2. 1 plus 1 minus 2 leaves no charge left over. So the HClO, the Cl is in +1. Now in HCl, H, as I've said before, is usually in +1 oxidation state, no charge left over, so the Cl must be in -1. +1 minus 1 leaves no charge left over. Give the two half equations. Remember, half equations, I've got electrons in them, E minuses, to show the oxidation reduction process that occur in this redox reaction. So first of all, I've got Cl2, chlorine, in oxidation state 0. If it's atoms or just an element, one symbol on its own, then it's in oxidation state 0. So that 0 in HClO is going from 0 oxidation state up to +1 oxidation state. If it goes up from 0 to 1, if the number goes up, the oxidation state goes up. That's oxidation. So this is the oxidation half equation where I've got Cl2 going to HClO. Now, Cl2 plus H2O, by the way. Cl2 plus H2O goes to ClO. So Cl2 plus H2O goes to CHClO. Now, I've got a bit of a problem here because Cl2 plus H2O, I've got too many H's. I'd have too many H's. Cl2 plus HClO. In HClO, I've got one H and one O, but in H2O, I've got two H's and one O. So I'm going to have to make H pluses. So there's a couple of rules to do with half equations. It always involves electrons, and we have to work out which side and how many. But you can also add H2Os. You're allowed to add H2Os, and you're also allowed to add H pluses. So at any time that you can't balance something, you can add H pluses or H2Os to balance it up. So I've got Cl2 plus H2O was making HClO. I've decided that I can't ever balance that because I've got H2O and I've only got one H on the right, so I'm going to make some H pluses. In making some H pluses, then I'm going to have to balance it. Cl2, 2 Cl's makes 2 HClO to balance up the Cl's. 2 O's mean 2 waters, 2 waters mean 4 H's. I've got 2 H's there, so I'm going to have 2 H plus. That's where the 2 H pluses come from. Now there's no charges on the left. There's 2 1 pluses on the right, 2 H pluses on the right. So to balance out the pluses and minuses, I'm going to need 2 minuses, 2 electrons on the right hand side. 2 pluses, 2 minuses make nothing to equal with the no charges on the left hand side. The reduction half equation, well, reduction is going down in oxidation state. So Cl2 going down to HCl where the oxidation state is -1. That's reduction from 0 oxidation state down to -1. So I've got Cl2 going to HCl. This time I don't need any O's, I don't need the H2O's because Cl2 going to HCl, I can just put H pluses on the left hand side. So I've got Cl2 going to HCl, I've got H on the right hand side, so if I just put H pluses on the left hand side, I'll get my H's balanced. Now I don't need the water at all because there's nothing on the right hand side with O's in it because HCl hasn't got any O's in it. So now what can I do here? 2 Cl2, 2 HCl, 2 H's, 2 H pluses, 2 pluses, 2 minuses. I need 2 electrons on the left hand side to balance out those 2 pluses. So that's my oxidation and that's my reduction. If I was to ask for an overall equation, so this overall equation, I'd add everything on the left. So Cl2 plus H2O plus Cl2 plus 2H plus 2E minus makes 2HClO plus 2H plus 2E minus and 2HCl, and that 2 electrons on either side would balance, and I would end up being able to simplify it to this. Chlorine is reacted with cold aqueous sodium hydroxide in the manufacture of bleach. Give an equation for the reaction between chlorine and sodium hydroxide. Basically, you've got to learn this. Sodium hydroxide is NaOH plus Cl2. Makes sodium chloride, normal salt, but NaClO. NaClO is your bleach, so that's the chemical that's in bleach, plus H2O, because the H's haven't been accounted for, so I need some H2O. So salt water, basically salt water and NaClO. So when you add sodium hydroxide and chlorine, you basically get salt water, normal salt water, and NaClO, which is your bleach. You'll need, you've got two NAs, so you need two NAs there, two O's, balance out the two O's, and the two H's balance as well, so 2 NaOH. Okay. I've got an overall equation, ClO plus 2I minus plus 2H plus, that makes I2 plus Cl minus plus H2O. A sample of bleach solution was found to contain ClO minus ions with a concentration. I've got a concentration of this. Potassium iodide is added to 20 centimetre cubed of this bleach. Right, so first of all, before I think about anything else, I've got a concentration and I've got a volume. If I can get that volume, centimetre cubed, into a larger unit value of decimetre cubed by dividing by 1,000, I can get that into decimetre cubed. I've got concentration, I've got volume in decimetre cubed. I can work out number of moles of ClO. So that's obviously where it's taking me first of all. 20 centimetre cubed, from centimetre cubed up into a larger unit value, centimetre cubed up into decimetre cubed, I divide by 1,000, so that's 0.02 decimetre cubed. Concentration, moles divided by volume, so 0.109, which is the concentration of the ClO minus, equals moles divided by 0.02, that's the volume in decimetre cubed. Multiply those two together, I've got the number of moles of ClO in this bleach. Okay, the next thing I've got to do is to work out if I've got ClO reacts with potassium iodide. It says the potassium iodide, the iodide ions are I minuses. So the potassium iodide makes I minus. But 1 mole of ClO reacts with 2 I minus. So I'm going to have to double this to work out the number of moles of I minus or potassium iodide I've got. So for the potassium iodide making the I minus, 1 mole of ClO minus reacts with 2 moles of I minus. So I'm going to multiply this by 2. And now I've got the moles of I minus or potassium iodide. I want to try and work out the mass of potassium iodide. Now I can work out mass because moles is mass divided by mR. Potassium iodide is Ki. I know that because I can see I is 1 minus. K, potassium's in group 1, so it'll lose 1 electron and become 1 plus. 1 plus 1 minus is just Ki. I'll look up the mass number of K, that's a 39, mass number of I is 127, add them together, I've got the MR of Ki 166. Moles is mass divided by MR, moles is 0.000436 because I've doubled the 218 times 2 because 1 mole of ClO minus reacts with 2 Ki. Equals the mass divided by the MR. Multiply these two together, I've now got the mass, 0.072376 grams. I might have to round that up to less significant figures in a minute, grams of potassium iodide. It wants it in milligrams, so grams into a lower unit value of milligrams, then I multiply by 1,000, multiply this by 1,000, it equals 72.376. Appropriate number of significant figures. All of the others seem to be to 3 significant figures, 0.0109, 20.0200, 3 significant figures, so I'll round the 376 up to 4, and 72.4 milligrams now is to 3 significant figures. What would I observe? Well, I2 is a black solid, and you get away with saying a black solid. However, if it's in water, it actually dissolves and forms a brown solution. You'll probably get away with both of those. Black solid made, yes, or turns brown, a brown solution, because it actually dissolves. But either are fine. Okay, let's just do spoilers on this one. Okay, potassium chlorate, KCl04, is used in fireworks. give the reaction of, it says it breaks down potassium chlorate 7. Let's work out where the chlorate 7's come from. Where does that 7 come from? Well, O is a -2 oxidation state because they're in group 6, so they gain 2 electrons to fill their outer shell, so they're each -2. 4 -2 is a -8. K is in group 1, so it loses 1 electron to fill up its outer shell. That's +1. +1 added to a number, -8 leaves no charge left over, so the Cl is in 7 because 1 adds 7 is 8 and -8 leaves no charge left over. So that's why it's chlorate 7. That 7 is the oxidation state of the Cl. Decomposes, breaks down, produces chlorine and oxygen. So I've got this KClO4, I'm given that here, so that's easy enough. Makes potassium chloride. How do I know potassium chloride is KCl? Because K is in group 1, forms a 1+ ion. Cl is in group 7, makes a -1 ion, 1+ and 1- KCl. Oxygen is O2, so KClO4 makes KCl plus O2. I've got 4 O's, so I need 2 O2. So that's where that balanced equation's come from. And I've used it here now because it's asking me for the enthalpy change in the question mark. Calculate the enthalpy change for this reaction that I've just done. So I'll do a Hess's diagram. So I've got enthalpy of formation. Remember, formation is formation of 1 mole of these substances from its elements in their standard states. So from K, potassium, from Cl or Cl2, chlorine, from O, oxygen, as you'd normally find them in the lab. Standard states is as you'd normally find them in the lab at normal atmospheric pressure and 25 degrees C. So I'd find potassium as K, it would be a metal. Cl, Cl2, chlorine gas, pairs up in 2s so that each of the atoms can share an electron each and fill their outer shell with a covert by sharing a pair of electrons in a covalent bond. And similarly for oxygen, except it shares, they each put 2 into the covalent bond. It forms a double covalent bond because oxygen's in group 6 and it needs to share 2 electrons each to fill up its outer shell. But anyway, these are the elements in their standard states as you'd normally find them under conditions of normal room temperature and pressure. And so you're making these chemicals here, KClO4, KCl, from the elements in their standard state. So I've drawn it out as a visual diagram called a Hess's diagram, a Hess's cycle. So let's have a look. So Hess's law says it doesn't matter which way round you come. So if you start here at KClO4 and come round to elements in their standard states and then come round this way, it doesn't matter that you're coming round this way. The overall enthalpy change will be the same as if you go straight across there. So coming round this way in an anti-clockwise direction, KClO4 to make the elements in their standard states, and then the elements in their standard states to make KCl and O2. That route is the same as that route. So Hess's law says that the overall enthalpy change is independent of the route taken. So I've got some of these, what I call jigsaw pieces, and I can put it together. I want to find this one. That's what the question's asking. Find that question mark. Now I've got the enthalpy of formation of KClO4, so from elements in their standard states here to make KClO4, and if I make 1 KClO4, 1 mole of KClO4, it's -434 kilojoules per mole, so it's an exothermic reaction going here. It says to make KCl it's -436, so using some of the K, some of the potassium K and the Cl2 to make KCl it's -436. Now oxygen to oxygen is itself, so there's no enthalpy change there because this is just itself, so that's a 0. Now if I come round this way, every time I go from here to here, I want to come round anti-clockwise. I want to turn this KClO4 into elements in their standard states. I want to come round this way, and then I'm going to use those 2 arrows in the same direction. I need to reverse that arrow, so instead of -434, it's going to be +434, +434, and then this arrow is going in the right direction, -436 and 0. So my answer is +434 -436 plus 2 lots of 0, or just 0 because there's no change there between the O2 going to 2O2, is -2 kilojoules per mole.